objective 3, we are going to learn again more story. Here he is explaining, actually the whole essence of this page will be left-hand rule. So I'm going to scroll down and show you right there, guys. Here he is explaining the left-hand rule, where he would show you the finger just like how I pointed this. So I'm going to show you how it looks like. This direction represents the direction of current and the field is in clockwise direction. If your current is in that direction, your field becomes counterclockwise. So, yeah, same thing dear. Look, if you go left here, lines of force are in the counterclockwise direction. The important part is, guys, this representation. Because in the exam, he'll say out of the 4 ABCD diagrams given, which one represents the right direction for left-hand rule. So the clockwise, as you guys can see, this is in the counterclockwise direction. He says indicates force direction with current going away from you, okay? And the direction of the lines are counterclockwise. Same thing here as well. So here he says lines of force in this direction here indicates force direction with current coming towards you. Okay, so all he's trying to say is if the current goes in one direction, your lines of force are in clockwise. If the current goes in opposite direction, you have counterclockwise direction for current flow. Sorry, lines of force. Magnetic coil property. So here he says, do you guys see? I want you to highlight this. This is the most, you can say, thing to understand in this whole module. So highlight these few lines. It says when 2 current carrying conductors are brought closer, for example, these are my 2 current carrying conductors, okay? Depending on whether both of them have current in the same direction or current is one going up, one going down, okay? If the currents are in the same direction, the fields get added. When 2 current carrying conductors are brought close, there is an interaction between the magnetic fields and those conductors. The type of interaction depends on the direction of current. If the direction of current in both conductors is identical, they will go and strengthen the field. If they are in opposite direction, you'll minus the field. So let's say field here is 10 coulombs, field here is 20 coulombs, we add them together, become 30. If this is 10 in one direction, then the opposite direction is minus 20, you get minus 10 coulombs. That's all is he talking about here. Whether you add them or you minus them depending on whether they're pointing in the same direction or they're pointing in reverse direction. So same thing here, guys. He's showing you magnetic lines of force going from North Pole to South Pole. 1 second. What else? The previous diagram, he was not showing any magnetic rod. He was just talking about electric field, that whenever you have current in one direction, your field is rotating in clockwise or counterclockwise direction. Here he is putting a magnetic rod in the middle as well to create electromagnetic field. Means electric field because of the current, magnetic field because of the rod. So you get electromagnetic field. Now he says electromagnet design considerations. What that means is you're designing an electromagnet. Okay, will it have a stronger field or less stronger field is dependent on these 3 you can say factors. So highlight the amount of current the coil is carrying, how many number of turns it has, and what is the type of the core. Depending on whether it's soft iron, hard iron, steel, the field, the intensity of the magnetic field will be different. So what else is he talking about here? Let's start with the first one. Current is 1 amps, current is 2 amps. Do you see how stronger the field is here compared to there? Second step, number of turns. More turns you have, more field you get. Third, air core compared to soft iron core. Which one is a better material for retaining the magnetic properties? Iron. So you see more field here compared to less field there. For material retentivity, when the material is chosen for the core of an electromagnetic device, it should have low retentivity. This means that the material will lose its magnetism as soon as the current through the operating coil is switched off. In devices such as door chimes, relays, solenoid valves, It's necessary for the armature to drop out immediately when the coil is de-energized, sure. But again, it all depends on what the application is. If you need a circuit where you need this equipment to always have magnetic properties, you will choose soft iron over air core. If the core material has high retentivity, it would remain magnetized even when the current is off and the device will not function properly. Now, last thing you want to learn in this whole chapter is hysteresis loss. All these definitions, that's the last definition. What is hysteresis? Hysteresis is, remember I showed you this curve? This curve is also called hysteresis curve. Okay? You gave some charge to magnetize it. It got magnetized to the highest point. Now you're demagnetizing it. The losses that happen on the way to magnetize the material and then demagnetize is called hysteresis loss. Okay? That's the story he must be teaching you here. If I were you, I will at least highlight the definition from this paragraph. Here it says, if the device is operated from an AC supply, the magnetic polarity of the core material constantly changes between the current direction because the current direction keeps changing at a rate determined by the frequency. This flip-flopping of the magnetic domains causes friction, which in turn produces heat. This is called hysteresis loss. In an easy language, the amount of loss that has happened because you magnetized something and now you're trying to demagnetize is called hysteresis loss. This loss is wasted energy. It shall be kept to a minimum. If silicon is added to the steel core material, hysteresis losses can be reduced. Just the story. What is an eddy current? Highlight this as well. When a conductive material such as iron core of an electromagnetic device is subjected to a changing magnetic field, voltages are induced. As a result, there is current flow in the core. Those are called eddy currents. I'm sure you would have heard of word called eddy current loss. You can't really ignore it because when you have an electromagnetic device, it will have magnetic field changing and that will create eddy currents. So any magnetic material has eddy currents. So the important term to be aware of is eddy current loss right here. Okay, I'm going to read the full paragraph, but you should highlight the whole thing as well. Alternating current supplied to the coil produces a constantly changing magnetic field, generates electrical currents. Current flowing through a resistance produces heat. The heat produced and subsequent energy lost due to the circulating currents is called eddy current loss. If the core is of a solid construction, eddy currents losses would be sufficient to cause serious overheating. How do you get rid of eddy currents? By using laminated core. I'm sure in transformers you must have seen that the core is laminated. That will help you reduce eddy currents to a minimum value. Now, he's talking about other losses. There is something called iron loss. Well, your core is made up of iron, so there will be losses because of that as well. Iron losses are total losses that occur because of the core. Iron loss, which is measured in watts, includes both hysteresis loss and eddy current loss. Now, saturation, we already talked about it. Objective 3, I'm going to move on to objective 4. Induced voltages. The important thing to know is Faraday's laws. Very, very important rule. Okay? I'm sure you would have heard of a term called E is equal to BLV. I hope he's showing. No, he didn't even show you here. Okay, for now we're going to highlight. I'll give you a full formula key as well. Faraday's laws of induction describe the amount of voltage that will be induced whenever there is relative motion between a conductor and a magnetic field. Amount of voltage induced in a conductor is proportional to the rate at which conductor cuts the lines of force. If the numbers of lines of force per second increases, amount of induced voltage will increase. When a conductor cuts lines of force at a rate of 100 million lines per second, 1 volt is induced. For now, just highlight, guys. I'm going to give you a formula key. It will make more logical sense. Left-hand rule, he's explaining one more time, Fleming's left-hand rule. So same thing. Now, this is what I was explaining you when we started this chapter. This thumb represents current, which is also called thrust or motion, whichever direction it's moving. Okay. This is 90 degrees to the direction of current. When your field is 90 degrees means if this conductor is this one and it has some kind of current going, there will be some field that will be induced around this magnetic core. Okay. clockwise or counterclockwise depending on the direction of this motion. Okay, so here I'm gonna just give you the formula now, because reading this story and looking at the formula, two different things. So guys, you're gonna copy this down on the notes right here. Fleming's left hand rule says that the formula E is equal to BLV. B is how strong the field is, L how long the conductor is, and V the velocity in which electrons are moving. These three factors affect how much EMF will be generated. And your notes here.
Is that a BLU?
V as Victor.
What's the first one there? B?
B as beta. This is actually not B, but beta, like that. Then L for length, V for velocity. How fast the electrons are moving. L, how long the conductor is. B, what is the magnetic strength of that magnet. All three factors decide how much voltage will be created. You'll be using this formula at least once in the exam. He's not given you formula, but I'm gonna give it to you by end of day today. So same thing here, guys. The formula I gave you, he gave you these three factors. So highlight. The EMF is based on flux density, means how good the flux lines are, means the magnetic strength. The number of turns in the conductor, and the rate at which lines of force are cut. L should be, yeah?
E is the amount of, the variable for the amount of EMF.
That's right. Means how much voltage is induced. So highlight this. Once we do the questions based on the formula key, it will make so much more logical sense, guys. I wonder why is he teaching you story and not giving you formula. So, I'm sure in objective 5, here he is talking about electromagnetic induction. It's also called EMI. So, electromagnetic induction. Let's say this is an electromagnet, okay, or this is just a piece of iron core. How would I induce to it has both electric properties as well as magnetic properties? Okay. First thing called self-induction. How do you self-induce rather than using a second device to create induction in the first one? How do you self-induce? Okay. So highlight the definition of self-induction. Here he says whenever there is relative motion between a conductor and magnetic field, of course there is some voltage that gets induced. If the current in a conductor changes, the magnetic field around the conductor changes proportionally. What he's trying to tell you is if you want to create an induction and an equipment, make sure that device has some magnetic properties and you pass current through it, it will create some kind of voltage. But what is mutual induction? Mutual induction is this device. So think about transformer. Okay, your primary is connected to the source. There is a core in between, and then you have your secondary. You give 120 in and you get 240 out, for example. How is voltage being induced on the secondary because of primary? This is through mutual induction. This guy is creating field in this guy. That's called mutual induction between two. Primary coil, secondary coil. Here he is only talking about self-induction, means if I have only one coil, how would I make this coil to have some kind of field? By making sure that this is an electromagnet and it can create some kind of field through passing current. So he's giving you all the steps to making an equipment more magnetized such that it has EMF properties. So here, that's all he's talking about, guys. He's creating some kind of flux by having, he's creating some kind of field and that creates some kind of voltage. That's called self-induction. Mutual induction between two people. Lenz's law, E is equal to BLV that I talked about is actually Lenz's law. It's coming up as you go along.
Do you suspect a number of questions on the test will pertain to magnetism?
Nah, I
Not
would
much.
say no. These three modules not super important. Magnetism, again, one question on E is equal to BLV. Second question on if I increase the number of turns, what will happen to the field? Like those more logical questions than this story.
So,
So
good, important to know, but don't focus all your studying on it.
on it, yeah, and it's again just the story to read, which logically doesn't make sense to a lot of students because unless you do some kind of math questions or a explanation to why you are doing what you are doing, it won't make any sense. That's why in the binder I have mailed you has some questions on calculation of based on Lenz's law and E is equal to BLV, where you will see I will give you V, I'll give you L, and I'll give you EMF. I'll ask you to find voltage. Those kind of questions will be based on the formula key. And I'll email you the formula key in a bit as well, guys, because in your module I don't see the formula key that you should have. Let's see what else. He's just talking about self-induction. After self-induction,